Well, let me tell you, human life would be impossible without both low and high mass stars. The long lives of the low mass stars allow evolution to proceed for billions of years, but only high mass stars produce the full array of elements on which life depends. Oops. So, remember that HR diagram, or the color magnitude diagram. So color goes from blue to red, temperature increases that way, and we have brightness increasing upwards. And remember that main sequence. So we talked about the low mass stars, say like the sun, so M star 1 to 2 solar masses. And then now we are going to talk about the high mass stars with masses at least 8 times the mass of the sun. They do some different things. The highest mass stars proceed to fuse increasingly heavier elements than the lower mass stars were able to produce. So we're going to see how that happens. Remember we said the low mass stars, they do not have enough gravity to be able to fuse elements heavier than helium, right? So they do produce some carbon, but that is about it. The fusion process stops there. Okay, so the first different thing about the high mass stars is that, well, the hydrogen does burn into helium. However, the burning or the fusion is a bit different. It turns out that in high mass star, the strong gravity compresses the hydrogen core to even higher temperatures than we find in the lower mass stars. And the hotter core temperatures makes it possible for protons to slam into carbon, into oxygen, into nitrogen nuclei, as well as into other protons. And so those particles in the core of the star interact differently, and the reaction of fusion of hydrogen into helium uses carbon and nitrogen and oxygen as catalysts. So here is a diagram that illustrates the 6 steps of the what's called now the CNO cycle, by which massive stars fuse, cycle of fusing hydrogen into helium. The overall result is actually the same as that of the proton-proton chain, if you remember from our discussion of the nuclear fusion that happens in the sun. So, but the different thing is that now carbon, nitrogen, and oxygen nuclei are catalysts. They actually help the cycle proceed, but are neither consumed nor created in the overall cycle. Take, for example, step 1. You have one proton or one hydrogen atom that's going to combine with a nucleus of carbon 12, an isotope, carbon 12, and they produce the nitrogen nucleus. and some gamma rays, some photons of light. Then this byproduct, the nucleus of nitrogen, is going to disintegrate into a different isotope of carbon, carbon 13, with the production of neutrinos and positrons. You've seen those particles before. And this carbon 13 is going to capture one proton, right, or the nucleus of a hydrogen atom in step 3, giving rise to a new isotope of nitrogen, nitrogen 14, plus some new energy in terms of light that is created in that reaction. In step 4, that nitrogen 14 nucleus is going to capture again another proton, and the end result of this is again some gamma rays, some light, and a new nucleus, the oxygen 15, which will disintegrate into the nitrogen 15, a new type of isotope, again a capture of a new proton, and finally gives rise to one nucleus of helium and another carbon 12 isotope that could continue this cycle by combining yet with another proton. So how many protons did we find here? So it was one here, and then second here, and then the third here, and then 4. So it is again 4 protons, pp, right, or hydrogen, and there are some other things, the catalysts, interacting in the meantime, but the end result, the product of all these reactions, is a new isotope of helium 4, right? So basically this is what's illustrated here. So there are byproducts, which is light or photons, gamma rays, and then positrons and neutrinos. Pretty much like we've seen it happens in the very core of the sun, where we have the process of nuclear fusion of hydrogen into carbon. Okay, so fine, we have hydrogen that in the core is actually going to run out because it's converted into helium. So very much like it happened in the low mass stars, right? We get very similar processes. So what do we end up with? An inert core. This is going to be inert. It's not going to do anything. No fusion yet, because it doesn't have enough pressure to increase gravitational pressure inward, to increase the temperature to levels that would allow for the helium to fuse into carbon. So what do we end up? So if we have here the luminosity or the brightness, we have again the temperature. So this is the HR diagram, and this was the main sequence, and this was the high mass star on the main sequence. Now it's going to become a red giant because of that shell of hydrogen burning. Okay, so it's going to move and become a supergiant. Move in terms of increasing luminosity and actually cooling down. After that, the helium will ignite in a core, so kind of like a helium flash, but it doesn't actually happening in the high mass stars. Helium burning in the core, hydrogen in shell, and that's going to be the horizontal branch. But now we have enough gravity to push in. The carbon core forms, and you end up with now a new phase, new super giant, and you have inert carbon core and then two shells burning, the helium and the hydrogen. And it turns out that the carbon has the possibility of igniting in the core. So now the carbon is going to turn into nitrogen because the pull of gravity, the inward pull of gravity, is strong enough to create high pressure and very high temperatures. So it's going to continue. It's going to continue like this. Now we have the carbon. It's going to capture one of those newly created helium nuclei and they form the oxygen. And then later on, that newly formed core of oxygen is going to burn by helium capture into neon, and then the neon is going to convert into magnesium, and so on. And because the core temperatures in these very massive stars allow fusion, because the temperatures are still very high, the pull of gravity still strong, therefore temperatures high enough, temperatures and pressures, to allow fusion of elements as heavy as iron. And the temperatures are actually even strong enough to allow iron fusion. How the fusion stops because, or the burning stops because the iron is or has the lowest mass per nuclear particle. Remember, the nuclei are made of protons and neutrons. And so because iron has the lowest mass, when you combine iron with something else, you actually get something with not less mass, but higher mass. And so this difference in mass is going to be negative, right? So is not produced anymore. That energy associated with that change in mass or difference in mass. So we end up with an inert iron core at the center because the burning cannot proceed, right? So iron fusion does not create energy. It actually needs energy in order to produce something of the heavier and heavier elements. And so iron will start building up in a core, And that's going to happen until the degeneracy pressure, about which we learned in the previous chapter, when we talked about the brown dwarfs, okay, will no longer be able to resist the gravity, okay? And now the degeneracy pressure is the only thing that can keep up or act against the gravity. But if the star builds more and more iron as it creates this onion shell structure of burning shells, right? So we have the outermost shell, that's hydrogen that's burning into helium, and then you have the helium burning into carbon, and then the carbon fusion, carbon burning into oxygen, and then oxygen into neon, and neon into magnesium, and so on, right? And then eventually oxygen and the silicon and all the other heavier and heavier elements until you get to the core of iron form, right? So that means the star starts creating more and more iron, but that stays inert. It's not able to produce anything that's going to keep up with the push of gravity. What's going to happen is the core would suddenly collapse under the push of gravity. It's going to be a lot of iron in that core. And that push, that collapse, gravitational collapse, is going to create what is called a supernova explosion. Supernova. Talk a little bit about that. Supernova explosion. So the thing is, while the iron core grows, it's going to crush down. That's what gravity does. And there's going to be a critical moment when the whatever was keeping all those atoms or nuclei of iron together, which was held actually together by the degeneracy pressure, that is going to fail, and it's going to be a runaway collapse. Okay, so the pressure goes away, and then the electrons and the protons are going to be so close to one another that a new strong nuclear force is going to be able to act and make them interact at the nuclear scale, and that is going to make neutrons and neutrinos. Now, neutrinos travel through pretty much everything. They don't interact much with anything, and so whatever it's going to be actually left is going to be basically a very dense soup of neutrons, which we call a neutron star. Okay, so while this gravitational collapse happens, there will be a very powerful shock wave that races up through the star and reaches the surface in about an hour, extremely fast, because it takes, all that collapse takes 1/10 of a second. And because of that shock wave, the star explodes. And that explosion is called a supernova. Nova means in Latin new, so it looks like a new star was born. So that's where the name is coming from. When people first observed this kind of phenomenon, they thought it was a new star that was born. Later on, we realized, well, that is actually the moment when a star dies. It's pretty interesting, isn't it? So, what's left, or what we see, is of that explosion is the spreading remains of the exploding star, and that is called a supernova remnant. And we have here a pretty nice image, obviously high resolution, very high quality, and it is actually a composite image of many filters in many wavelengths. So this is called the Crab Nebula, because it kind of looks like a crab, and it's the remnant of the supernova seen in the year AD 1054, so really long time ago. Okay, now a very important note: the energy and the neutrons released in any supernova explosion, actually, based on our calculations and calculations of the so-called astronuclear physicists, showed that it is this kind of explosion that are pretty much the only phenomena that enable elements heavier than iron to form. For example, the gold and uranium, right? So remember how I said there are all kinds of things. Everything that is not hydrogen and helium, it is formed in stars or by stars. But we've seen that even the high mass stars cannot produce anything heavier than the iron. It is actually true. During the supernova explosion that elements heavier than iron are created in this. If you wonder about the energy budget, like what's coming out of this kind of reaction, this kind of phenomenon, there are a lot of neutrinos, and we have detected them. So we do have observational evidence for the fact that any kind of supernova explosion, so death of very massive stars, is actually accompanied by a shower of neutrinos, and that accounts for 99% of all of the energy that is produced by this event. There is very little light, although that's the only thing that we see with in the visible wavelengths, or actually on all wavelengths. The whole electromagnetic spectrum emitted by this event accounts for only 0.01% of all of the energy that is created or released, converted, right, in through this kind of event. And then there is the energy associated with the shock wave, and that accounts for 1%. Do you wonder how many of these supernovae we expect to happen out there in the universe? It turns out that there are quite a few, or just a few supernovae per century per galaxy. Okay, and many of the supernovae we are aware of have been seen in other galaxies. In the Milky Way, the last one that we have witnessed or have observations and evidence for was about 4 centuries ago. So we're actually kind of due for a supernova happening in our own galaxy. And so the astronomers are actually keeping their eyes very open for red giants to go poof. And yeah, of course, for a supernova, we wouldn't even need a telescope. It's that luminous. Okay, so this is an example of the supernova 1987A. This is the year in which it happened, and it's A because it's the first that happened in that year, and that went off in the Large Magellanic Cloud, which is a dwarf galaxy that's neighboring our own Milky Way. It's basically the closest supernova in the last 4 centuries. So just before the explosion, it was basically nothing, and that appeared 3 hours after an antineutrino burst was detected, and that lasted about 10 seconds, and that is the supernova explosion. That's pretty neat, isn't it?